Modern smartphone cameras are smaller than a coin, yet capable of capturing images once possible only with professional.
At this scale, even a single dust particle can permanently damage image quality. That is why camera modules are built inside.
Smartphone cameras operate at micron-level tolerances. Lens position, sensor distance, and alignment must be exact.
Image quality does not come from size alone. It comes from optical design, precision alignment, and intelligent manufacturing.
A camera sensor does not see images. It detects light. Millions of microscopic photodiodes measure bright.
Human hands are not precise enough at this scale. Automation ensures every component is placed with repeatable accuracy, thousands of times per hour.
Unlike standalone cameras, smartphone modules cannot be adjusted after assembly. Every module must be perfect before it leaves the factory.
What looks simple from the outside is one of the most complex manufacturing processes in modern electronics, and it all begins with optics.
Intervals. Smartphone camera lenses begin with ultra-pure optical glass. Unlike plastic, glass maintains clarity.
Glass is first cut into rough lens blanks. Each piece is measured precisely because even small variations affect.
The blanks are heated and pressed into precise molds. This process defines the lens curvature, which determines focus, sharpness, and distortion control.
Lens curvature is measured in microns. Any deviation changes how light converges on the sensor, affecting sharpness and color accuracy.
Grinding refines the lens shape further. Each stage removes microscopic imperfections. Polishing creates optical clarity. At this stage, surface roughness is reduced to nanometer levels, allowing light to pass cleanly without scattering.
Every lens is inspected. Only those that meet strict optical standards move forward. Imperfect lenses are rejected immediately.
At this point, the lens is perfectly shaped xylene, but not yet complete. Next, invisible coatings will enhance.
Even after shaping, the lens is not optically perfect. Microscopic surface roughness can scatter light and reduce sharpness.
Polishing is performed in multiple stages. Each step removes smaller imperfections than the last, gradually refining the.
Interferometric scanners measure surface accuracy using light itself. Variations smaller than a wavelength are detected.
Bare glass reflects a significant amount of incoming light. Without coatings, internal reflections reduce contrast and introduce glare. Bare glass reflects a significant amount of incoming light. Without coatings, internal reflections reduce contrast and introduce glare.
Lenses are coated inside vacuum chambers. Ultra-thin layers of material are deposited atom by atom, forming anti-reflective and color-correcting coatings. Multiple coating layers are applied. Each layer targets a specific wavelength of light, improving color accuracy, contrast, and low-light performance.
Uniformity is critical. Even a slight variation in coating thickness can affect image consistency. Automated systems verify coverage across every lens.
Every smartphone camera relies on a single critical component to the image sensor. Unlike lenses, which shape light.
Image sensors begin as ultra-pure silicon wafers. Any contamination at this stage would permanently affect image quality. Purity is non-negotiable.
Using photolithography, microscopic patterns are etched into the silicon. These patterns form millions of photodiodes, the pixels that detect light and color.
Each pixel acts like a tiny light bucket. It measures how much light hits it and converts that information into
Before sensors are separated, each wafer is tested. Defective pixels and electrical faults are identified early, ensuring only high-quality sensors move forward. The wafer is then cut into individual sensor chips. Precision here prevents cracking and preserves electrical integrity at microscopic scales.
At this stage, the sensor is complete. It can detect light with remarkable accuracy. Next,
results. Every smartphone camera relies on a single critical component, the image sensor. Unlike lenses, which shape light, the sensor.
Image sensors begin as ultra-pure silicon wafers. Any contamination at this stage would permanently affect image quality. Purity is non-negotiable.
Using photolithography, microscopic patterns are etched into the silicon. These patterns form millions of photodiodes, the pixels that detect light and color.
Each pixel acts like a tiny light bucket. It measures how much light hits it and converts that information into an electrical.
To see color, sensors rely on microscopic filters and microlenses. These direct specific wavelengths of light to each.
Before sensors are separated, each wafer is tested. Defective pixels and electrical faults are identified early.
The wafer is then cut into individual sensor chips. Precision here prevents cracking and preserves electrical integrity at microscopic scales.
At this stage, the sensor is complete. It can detect light with remarkable accuracy.
A smartphone camera does not rely on a single lens. It uses a precisely stacked optical system where each lens element shapes light in a specific way.
Lens elements are placed by machines, not hands. Robotic systems position each lens with repeatable accuracy, down to a few microns.
Each lens in the stack corrects a specific optical error, distortion, chromatic aberration, or focus shift.
Lasers are used to align the lens stack precisely with the sensor. The system adjusts position and tilt until light converges perfectly on the pixel array.
Calibration occurs at the micron level. Movements smaller than a human hair determine whether images appear sharp or soft.
Once aligned, the lens stack is permanently secured. Specialized adhesives lock the optics in place without introducing stress or distortion.
After assembly, each module is tested optically. Machines verify focus accuracy, alignment.
Lenses are clear. With lenses and sensor perfectly aligned, the core of the smartphone camera is complete. Next, motion control.
Even the smallest hand movement can blur an image. At the scale of smartphone optics, motion measured in microns is enough.
And in coil. Autofocus relies on motors. By using electroforce, these motors move. Autofocus is calibrated automatically. Machines measure how light converges on the sensor and adjust lens position until focus is exact, often within a few microns.
Optical image stabilization works by moving the lens or sensor to counter hand motion. Instead of correcting blur digitally, OIS corrects.
Tiny gyroscopes detect motion thousands of times per second. This data tells the stabilization system
as the phone moves, the lens moves in the opposite direction. These adjustments happen in milliseconds, fast enough to keep images sharp even in low light.
With autofocus and stabilization calibrated, the camera can now react instantly to motion. Next, the entire mod.
Once assembled, a camera module must be sealed permanently. At this scale, even a single dust particle trapped inside.
Clean rooms control the direction and speed of airflow. Air constantly pushes particles away from sensitive components, preventing contamination during sealing. Specialized adhesives are applied in exact quantities. Too little and the seal fails. Too much and internal stress can distort the optics. Sealing presses lock the module's alignment permanently. Once closed, lens position and stabilization systems must never shift again. Adhesives are cured using controlled energy, often ultraviolet light or heat. This hardens the seal without introducing vibration or thermal shock.
After sealing, modules are inspected again. Optical systems search for trapped dust that could compromise image quality.
Sealing also protects against moisture and temperature changes. Environmental tests ensure the camera performs consistently across climates. With sealing complete, the camera module is protected for life. Next, every module must prove it delivers accurate color, focus, and performance.
Even perfectly built camera hardware cannot perform accurately on its own.
Focus calibration ensures the camera knows exactly where sharpness begins and ends. Machines analyze how light converges and color calibration trains the camera to see colors accurately under different lighting conditions. Daylight,
white balance, and exposure are mapped precisely. This prevents color casts and ensures brightness remains consistent throughout, even when scenes change rapidly.
Low light testing pushes sensors to their limits. Engineers measure noise, sensitivity, and stabilization response.
Lenses are checked for distortion and edge sharpness. Calibration ensures straight lines remain straight thus, and detail remains consistent from center to corner.
At this point, the camera knows how to see. Calibrated, verified, and optimized, it is ready to be integrated into a smartphone. At this stage, the camera module is complete, but not yet ready for use. It must be prepared to integrate seamlessly into a smartphone's electronic system.
Flexible connectors carry power and data between the camera and the phone. These connections must remain stable despite heat, vibration, and long-term use.
Shielding protects the sensor from electromagnetic interference. Without it, signals from nearby components could distort images or disrupt autofocus.
The housing protects the camera from mechanical stress. It maintained alignment and absorbs vibration once the phone is assembled.
Even after assembly, cameras are inspected again. Final optical checks confirm that nothing shifted during integration.
Power tests ensure the camera operates within thermal limits. Heat must be managed carefully to protect image quality and electronics. Only fully verified modules are approved. Any deviation leads to rejection, ensuring consistency across millions of devices.
Now complete, the camera module is ready. Next, we'll explore why smartphone cameras continue to improve also, even as they get smaller. Smartphone cameras improve not by chance, but by design. Each generation builds on tighter tolerances, better materials.
Hardware defines what a camera can achieve. Better optics, cleaner sensors, and more stable mechanics raise the ceiling for image quality.
Calibration connects precision hardware to intelligent software. By mapping how each module behaves,
Performance data feeds back into manufacturing. Tiny variations discovered during testing guide future refinements, closing the gap between design and reality.
As cameras become smaller, stability becomes harder to achieve. Advances in materials, motors, and sealing allow precision.
Modern photography blends optics with computation. Precise manufacturing ensures sensors and lenses provide clean data, giving software the best possible foundation. Millions of cameras must behave the same way worldwide. Consistency is achieved through automation, verification, and zero-tolerance quality control.
What fits in your pocket is the result of extraordinary precision.